Thanks, Fred. And Fred, maybe I can, well, I can't see anybody else's chat. If you do have a message for me, I can see yours. But for those attendees who managed to turn up, thank you very much for taking the time to leave your coronavirus infected workplaces and learn about probability plotting. And when I say learn about probability plotting, it's just an overview of some high-level techniques, but more importantly, where things can go wrong. So my next slide was supposed to be a general question about what I was asking all attendees. What is probability plotting? Because I can't see your chats or your responses, this might be a little bit of a challenging open general question to ask and answer, but I often see probability plotting interpreted as an activity which is intended for different things. Depending on who you speak to, probability plotting is line fitting, it is statistical analysis, it is part of reliability analysis, so on and so forth. So let's just leave that as an open question for right now, and let's just go into a slightly different, well, let's look at this from a slightly different perspective. I'm going to start with pointing out that human beings are good at identifying straight lines in things. So just bear with me in terms of where this is heading. We as human beings are really good at identifying patterns, and the easiest pattern to identify is a straight line. So if we have points in a straight line or dots in a straight line, we are really, really good at working out or being able to see if that line is really, really straight or true. And some of us are really so good that if the line bends, we can even have a good estimate at what the deviation is away from what is straight. Some people might be able to say this angle is around 12 degrees, for example. So human beings are really good at identifying straight lines and things, but we are bad at identifying different curves. So if we go back to our two straight lines, it's really easy for us to see a deviation away from straightness. But have a look at this curve. Can anyone see anything different between, or can anyone see this curve change at all from one region to the other? And it's very difficult for us to be able to do this, especially in a quantifiable way. In this example, we actually have two curves here. One part of the curve is based on a radius of a circular arc with a radius of 3. Well, the other is based on a circular arc of radius of 4. And that's very hard for us to pick up because we are not good at identifying different curves. So let's just understand, let's just put that conversation on hold for a minute. And let's go to let's look at what happens when we do reliability testing. So we typically have some sort of random variable we're investigating, which is often time to failure, and we might do some tests or get field data or just somehow observe the random process that is failure. When we do, we get a bunch of data points. In this case, we have 100 data points. And what we want to do with these data points is analyze them to try and understand the nature of the random process which is governing where these lie. For a time to failure, we can't know with absolute certainty when failure will occur, but it's very important to understand the nature of that uncertainty for reliability questions and decision making. And so what we can do though is do some non-parametric analysis, and we might create a histogram based on this data, and you can see there's sort of a bell-ish shape here. Everyone knows what the bell curve is, but we might say this looks roughly like a normal distribution, or this might look like a Weibull distribution. In this case, this Weibull distribution over here is a shape parameter of 5.28. And for those of you who aren't aware of what these distribution thingies are, all distributions are essentially sets or structures which allocate probability to certain outcomes. So in these two curves that look like bells, they're essentially saying the values that are closer to the values that are closer to the center of the bell shape are more likely to occur. So let's go back to our data points, our 100 data points, and when we come to analysis, we typically label them from smallest to largest because that allows us to rank them and create another question, another chart. In this case, we can create an approximation of what we call the cumulative distribution function, which essentially tells us the fraction of things that have failed with respect to usage. And here are our two shaded curves that are equivalent to those bell curves we just saw. And it's very hard to see, but you can sort of see that the CDF curve is much better at creating a smoothish line than our histograms were. You could see the histogram look like witch's teeth. They were some high columns, some low columns. It's very hard to discern the underlying distribution based on those columns. So the CDF is typically what we prefer to use. And what we can then do after this is we can scale our chart in a particular way. And you can see you applied a really weird scale on our y-axis, or vertical axis of CDF. And in this case, we've created a logarithmic scale on the horizontal axis. And we do this because if the data, or at least in this particular scenario, because if the data creates a straight line, we can prove mathematically or statistically that this is equivalent to the random nature of, in this case, a Weibull distribution, one of those example probability distributions we looked at previously. So we might be able to look at this and say, you know what, this data is pretty straight. So therefore, the Weibull distribution is a more correctly candidate probability distribution to describe our underlying random process. And so this weird chart with these weird axes are often plotted on papers, and we call them Weibull distribution plotting papers. And these are very useful before we had computers and other things which could do this all automatically, because it allowed you to do this by hand. And depending on which distribution you were trying to investigate, you'd have a different sort of probability plotting paper. And this scaled paper or scaled set of axes allows us to investigate if the data points are described by a normal distribution, the bell curve. And the log normal distribution is another probability distribution, and it too has its own probability plotting paper. So let's go back to our Weibull distribution plotting paper with our data points that seemed to create a straight line. Now, let's use these same data points and put them on a log normal distribution probability plotting paper. And in this case, I hope you can agree with me that this creates a curved line. So we can conclude relatively comfortably that the log normal distribution is not a good candidate probability distribution for our random process. But let's see what happens when we put our data on the normal distribution probability plotting paper. And you can see this also creates a relatively straight line. So this is also a good fit, or more correctly, a candidate probability distribution for our random process. Now you can see here that data can create straight lines, or what appears to be straight lines, on different axes or different probability plotting papers. So we might have at certain levels equally valid candidates, and it shouldn't be surprising because the Weibull distribution does approximate the normal distribution in certain circumstances. And this is the heart of probability plotting. We try and put our data onto axes that if the underlying distribution is true or is a good model for what's happening, we tend to see straight lines. So I haven't heard anything from you, Fred, yet, but do we have any questions that people are asking, or is this so boring and so basic for our audience that it seems to make sense?
No, I haven't seen anything yet. So no, it makes, and what you're talking about makes sense to me too. So yeah, drive on.
No worries. Please, notwithstanding that, it seems like our computers are also self-isolating within this with this webinar software, for maybe due to coronavirus. So please try not, if there's any questions, please don't hesitate to ask Fred, and he'll get them to me one way or another. So probability plotting, to answer that question that we talked about up front, is a graphical technique for comparing two data sets. This is a very technical term, because what this actually means is we want to compare one empirical data set, or typically we want to compare one empirical data set, what we observed through a test or field data, with a theoretical data set, which is a log normal distribution, Weibull distribution, or normal distribution set of random variables. And we scale different plotting papers for specific probability distributions. And as we just talked about, if the plotted data creates a straight line, it suggests that the underlying random process is described by that specific probability distribution. So, and there's a ton more plotting papers out there than the three we just talked about. These are the most popular. And of those three, the most popular of the most popular is the Weibull distribution. But in short, regardless of which paper you're using, which probability distribution it aligns with, it has a particular scale for the reliability of the CDF and the random variable. And so if you get that straight line, we can conclude with some level of assurance that that probability distribution is going to do a good job of understanding our failure process. And if we have a curved line, we can potentially exclude this probability distribution from further consideration. As I said, the most popular is the Weibull distribution probability plotting paper, and we'll explore why that is in a minute or later on in this webinar. And the really good thing about most probability plotting papers is that we're able to estimate the parameters directly from our probability plot. What are our parameters? They're the numbers that define the specific nature of our probability distribution. So let's look at our Weibull distribution probability plotting paper in greater detail. And you can see an example here. The vertical axis is the cumulative distribution function expressed as a percentage. It's a pretty weird shape. We can go through the mathematics in a different conversation, but you can see that down the bottom, around the 1.5, 0.3, 0.2% marks, you'll see that it is a very, very, very small scale. In the middle, around the 50% mark, you can see that there's 10% deviation, which doesn't take up much vertical displacement on the paper. The usage metrics, which you put down here, which could be cycles or distance or time to failure, is expressed in terms of the logarithmic scale. Now I can see a question coming through for the y-axis. The answer to the question about the mathematical approach is that the y-axis is the natural logarithm of the negative of the natural logarithm of 1 minus the CDF. So that's how you get this really weird scale. So it is sort of a log of a log, but it's important important to note that it's a natural logarithm of the negative of the natural logarithm of the 1 minus the CDF. And the next thing we add to our plotting paper is this stuff up here. These numbers on the top of our paper are used to estimate the Weibull distribution shape parameter, which sort of describes what that shape looks like. And it can be a bell curve, it can be flatter, it can be much like the exponential distribution. It can be like the gamma distribution, so on and so forth. And we'll go to how we use these numbers in a minute. And we have this line here, which helps us estimate the Weibull scale parameter. Now, for other probability distribution plotting papers, the y-axis, the CDF scale, is a function of the CDF function itself. For the normal distribution, for those of you who are aware of it, it's based on the inverse standard normal distribution function. So I can see another question coming through. I need to make my chart a bit bigger. So the question is, does having a straight line of data points for any probability distribution make the parameter estimation easier? And is that one of the major reasons that we prefer a straight line distribution? Well, to go back, if the line is not straight, the first thing it suggests is the probability distribution associated with that plotting paper is not a good model, does not describe the failure process anymore. So it's not, we don't want straight lines because they're good at helping us estimate parameters, even though that is the case. We're interested in a straight line because that tells us if the probability distribution is a good fit in the first place. And if it's not a good fit, you see that curved line and you, in principle, exclude that probability distribution from further consideration. So, but that's a really good question. It's really important to understand the thing we want is that straight line, because statistically it means that in a way, at least partly validates that probability distribution. So if we look at our paper, if we look at our paper here, why aren't you moving forward? There we go. This is all about the slope of our line. And if we can see that slopes in this region indicate what we call an increasing hazard rate, things are wearing out. And slopes in this region indicate a decreasing hazard rate, or things are wearing in. And we'll come back to this bit in the middle in a minute, but you can see that the line that sort of demarcates these two regions is the line associated with a shape parameter of 1. And we're going to go through an example shortly. So here's our probability plotting paper. We've labeled the horizontal axis, and we've done some reliability test, which is our test we ran before, and we plot it on this chart, and this is what it looks like. So if we run a straight line through here, through our data points, we then essentially move this line, or create a parallel line which goes through what we call the estimation point over here. And where our parallel line crosses with the top of our paper, that point is then correlates with the numbers on top of our paper for us to get an estimate of the shape parameter. In this case, this plotting paper suggests that beta, which is the shape parameter for our Weibull distribution, is approximately 5. The next thing we need to do is go back to that blue line we just talked about, plot across to the intersection of our line of best fit, then we draw a line straight down, and this gives us the second parameter of our Weibull distribution, which in this case is eta. So with these two parameters, this plotting paper, which suggests that the Weibull distribution is a good fit if you agree that the data follows a straight line or creates a straight line. Now we have the parameters for what we think is the best Weibull distribution to describe our data. And so this is the secondary benefit of having straight lines, and most plotting papers allow us to estimate these parameters directly. So let's go back to our raw data, which is the same raw data we talked about earlier. Here's our histogram, and let's see what the Weibull distribution with a shape parameter of 2 and a scale parameter of 5, other way around, shape parameter of 5 and scale parameter of 2 looks like. And you can see that this seems to be a relatively good fit, but you can also see that the histogram is not really easy for us visually to make a good subjective assessment about whether our random variables, or random data points, match our smooth probability density function, our bell curves, if you like. So the aim of probability plotting paper, the rationale of probability plotting papers, or the tenet, is that firstly, human beings are good at seeing lines. Secondly, human beings are really good at seeing straight lines. And thirdly, if we're able to find that there's a mathematical or statistical relationship between the straight line of a CDF in a particular scaled way, we can then make an assessment about the validity of the underlying probability distribution. So that is, in essence, what probability plotting is all about. So we use the Weibull distribution probability plotting paper because it can mimic a large range of probability distributions. You can see that in our example up front, it seemed like a set of data which was well described by the normal distribution was also really well described by the Weibull distribution. And we can immediately tell if the failure rate is increasing, constant, or decreasing. You might recall that we talked about the shape parameter. If the shape parameter is greater than 1, we know things are wearing out. And the shape parameter in our little example we just looked at was 5. So we know that things are wearing out. And every time you see a bell curve which describes time to failure, we know that the underlying process is wear out. Okay, and the last reason we want to use, we like using Weibull distribution probability plotting paper is we can estimate parameters really, really easily. Okay, so I was wondering if there is another question coming through. I see one. Sorry, Fred, it appears as if my chat window doesn't automatically scroll. The audience question, what is the minimum data points needed to get a good estimation? And I think, Fred, you suggested 20 is a bare minimum. I'm actually going to come back to that because it's a good question. And later on in the webinar, we actually look at the heart of that question, which is how certain can we be of a certain of any conclusion based on the number of data points we have. So it's a really good question, and I'm going to deal with it more in greater detail later on. So ordinarily, there are 8 steps to probability plotting, and they are all subject of a specific lesson, which we're not going to go through right now. There's a certain number of steps, there's a certain number of things you need to consider when you go through probability plotting by hand, at least, and that is a subject of another lesson. It essentially teaches you how to go about the process of using your data to create those dots on probability plotting. Okay, so the next, in a separate lesson I run, we go through and we create an example for probability plot based on data, and here is that data here. So if you were to sit through that lesson, the last slide, the last thing you would do would be create this data point, this probability plot, and we would use it to estimate that our shape parameter or beta for our Weibull distribution is about 1.6, and our scale parameter is 0.92. And again, the probability distribution is simply a structure or a framework which assigns probability to certain random variable values. So if we know the probability distribution, we can ascertain or understand, or at least have some inkling about the nature of failure. When are things more likely to occur? How many things do I expect to fail within the warranty period? At what stage will 5% of my fleet have failed? So on and so forth. Now, this so far we have talked about we've talked about straight lines. But in the next section, we're going to be talking about having multiple straight lines, which sounds a little bit antithetical, but we're going to go there anyway. I see that someone has suggested too that why is the horizontal line at 60%? So that blue line. Now, that's a really, really good question. The reason why that blue line is at 63% to be exact is that it just so happens that it's that the Weibull distribution, the equation for a Weibull distribution, regardless of the parameters involved, they all happen to pass, the CDF specifically happens to pass through the scale parameter value at 63%. And that's really, really useful. So regardless of the shape parameter, they will always go through the straight line will always go through this line of 63%. So what that means is that mathematically, we just need to find that intercept, plot straight down, and we'll get the the scale parameter estimate. So another question is, going back to estimating our shape parameter beta, how do we determine the y-axis intercept to move the parallel line to? Again, that's a really good question, and we always move that back to what we call the estimation point, which is right here, where that blue line we just talked about hits the y-axis. That's called the estimation point. So we create that parallel line which passes through that estimation point, and when that line intersects with the top of our probability plotting paper, we can then estimate directly what the shape parameter is. So I'm just going to quickly try and scroll and see if there's any more questions. No one talked about how you can use Y-Bayes, which is a different approach. We use Bayesian analysis as well. Probably won't talk about that too much in this webinar for time restrictions, due to time restrictions, sorry. But yes, it is an approach where you can use essentially a subjective or prior information about the underlying parameter values to essentially drive down the amount of information you need to make a conclusion about anything. But again, that'd probably be the subject of another lesson. Another question is, in addition to the characteristic life, could we obtain the mean time to failure, 50% failure from the Weibull plot? For the exponential, the MTTF is the same as eta. Does the plot confirm this? So the question is actually got it's a really good question, but there's a slight inconsistency. The mean time to failure for the Weibull distribution is not when the 50% of our things have failed. Again in the lesson I would cover where we talk about the probability plotting. It's an equation you use. You substitute in the beta and eta values, and it gives you the mean. What you're talking about for the time to failure of 50% of your items is the median. And you can estimate that directly from your plot. So excuse my not very accurate drawing, but let's just say I'm going to erase that ink. But if I just circle here 50% on the y-axis, I can then draw a line straight across my 50% line. Well, that's not very straight. Hopefully you can see what I'm trying to do though. And where it intersects our line of best fit, we go straight down, and this point down here is where we would estimate our 50% of our things to have failed. So I apologize for those lines not being very straight, but hopefully you get the idea. So for the exponential distribution, the MTTF is the same as eta, which is not the time at which you expect 50% of your things to have failed. But if you have picked up on something thus far, when we have a hazard rate or a shape parameter of 1, that is equivalent to the exponential distribution, in which case eta becomes the mean time to failure for the exponential case only. So hopefully that's a long-winded answer solves that question. Another question is, which points to be joined? If I join first and last points, the slope changes. And here you see a problem with probability plotting. Essentially, it's subjective. The line of best fit can change from person to person. And software is one way of getting around this. Regression analysis can help you create that line. Another approach is a maximum likelihood estimate. But we'll get to that in a minute. Actually, it's a really good question for us to hold because I have some material which will hopefully cover off on that. So let's have a look at the next bit where I talked about having potentially more than one failure mode on one chart. So let's have a look at this data here. Now, you might say, okay, this doesn't create one single straight line. And you're right, in this case, you might be able to argue that it creates 3 straight lines. And in each case, each straight line has its own shape parameter estimate. So the straight line on the bottom left-hand side has a shape parameter of 0.4, which suggests that the thing is wearing in, the product is wearing in, and then it moves into a region where the shape parameter is 1, which means it implies it has a constant hazard rate. And you can see that the thing is starting, your product, your system is starting to wear out as it transitions from the second one to the second straight line to the third straight line. So around about there is where wear out, at least based on the assumption that these straight lines are valid, this is where wear out starts to be your dominant form of failure. So you can then sort of potentially allocate or break down your Weibull plot directly into 3 different failure modes. And what this allows us to do is align them with the bathtub curve, the classical bathtub curve, or more correctly, the weird and wonky bathtub curve that would be more likely to describe the failure characteristics of your system. But you should be able to see, at least from a very high level, if wear out is starting to occur, if your Weibull probability plot is starting to have a higher and higher gradient. So let's look at this in a bit greater detail, and I want you to not start looking for things that aren't there. So what I'm going to do now is actually create a system which has 3 series components, and this is going to represent this system with this basic fault tree diagram here. And these 3 components, so what that means is that the system will fail whenever one of your components fails. And so this one over here, this component over here, it wears in or experiences infant mortality. And this one here has a constant hazard rate, and this one here wears out. So let's simulate the failures of this system and see what happens with respect to our bathtub curve. So this is the actual bathtub curve for this system. You can see how on the left-hand side, the component that is wearing in dominates failures. The component in the middle over here dominates failures, and then the one that wears out, it starts to dominate failures over here, because this is our hazard rate, the bathtub curve, the rate at which things fail. And we also know that for virtually all infant mortality or wear-in scenarios, the shape parameter or the slope of this curve is always between 0.3 and 0.5, whether it be small satellites, reliability growth testing, maintenance-induced failures. It is always between 0.3 and 0.5, typically 0.4. Now, let's simulate the failures for this system. And these red dots over here, which hopefully you can see, represent a single failure for our system. And you can see that our system is almost exclusively failing in region 1, because the whole bathtub curve, the whole hazard rate curve, is very relatively high. So what happens if we compare this bathtub curve with a lower rate but the same shape? So essentially it's going to move this entire shape down so that we see what happens to the failures that this causes. And as you might not necessarily intuitively expect, even though we have the same shape, because it's at a lower magnitude, our system is more likely to get through the maintenance-induced failures or the infant mortality or the wear-in region of our hazard rate curve, and they start to fail in what you might argue is more the region 2 part of the bathtub curve. So let's do this again. Let's actually compare this with the same shape, but the magnitude is driven down further. And the failures in this case are starting to occur on the upswing, the back end of the bathtub curve. So we have 3 bathtub curves, and each of them have the same shape, but depending on the overall magnitude of these bathtub curves, or the sort of average hazard rate, for lack of a better term, it really drives which region your system's going to fail in. Just because you have a bathtub curve which has 3 regions doesn't mean your system's going to actually experience a lot of failures in all of those regions. So let's just take this information, look at it in greater detail. For our first scenario, over half of our failures were from region 1. In our second scenario, with the same shaped bathtub curve, driven down a little bit, almost all of our failures were driven by region 2. And in this one over here, over half of our failures were driven by region 3. So the wear out failure mode. So this is all simulated. This is, in a way, actual data. This is what we actually get, or we actually observe, when we have these particular bathtub curves. So of these particular failure breakdowns, the bits where there's wear out, they're the things that we can address through things like preventive maintenance. You can do servicing before things start to wear out to address issues with your system. So let's see what the Weibull plots for all our failures for each different scenario looks like. So you can see that on the left-hand side, as you would expect, failures are occurring earlier because this is for the hazard rate curve, which has the highest magnitude. And this is the one where we experience mostly region 1 failures. For the second and third ones though, even though there is distinct difference in the nature of failures, one is primarily region 2 or constant hazard rate failures, the other one is the majority of failures are due to wear out, they have relatively similar slopes. If we do the shape parameter analysis in this case, you can see that yes, as we would expect in the case where we had that very high bathtub curve, infant mortality was driving the majority of failures. So the shape parameter is less than 1, which means that we can assume that there is an element of infant mortality. But for second and third lines, even though they're describing different scenarios, the shape parameters are relatively similar. And that's based on the line of best fit from the person doing the probability plot. And as a rule, you wouldn't, if you had a shape parameter of 1.18, you would not necessarily think that wear out failures are a huge issue. But in this example, over half of all failures are caused by wear out. So this is an example of where looking at what Weibull plotting doesn't give you the entire picture. So you need to be really careful. As a rule, this is too close to 1 for anyone to typically think, at least the way we are taught these days, to look at preventive maintenance or servicing, even though 53% of failures are wear out. And regardless of industry, if half your things are failing due to wear out, you would most likely do something about it. So Weibull analysis is just the beginning. You need to understand why failures are occurring. Before you can't just look at a Weibull plot and then assume you know everything there is to know. The Weibull plot is immensely useful for giving you the starting point for the next more physical or more scientific analysis. And because of this, if we just rely on Weibull plots for preventive maintenance interval estimation, we often get ourselves in trouble. So let's go back to our scenario where we had that very high bathtub curve and where things were failing almost exclusively in region 1. Surely this is something we don't observe in real life. That's not true, not even a little bit true. So these are the actual curves for post-servicing failure rates for an Australian military vehicle, which we did an analysis on. And you can see that these vehicles were, the bathtub curve caused by servicing was so high that virtually every failure was occurring in region 1 or infant mortality area. So what we were able to do was, by doing less preventive maintenance, we improved reliability by 23%. So we spent less money on maintaining the vehicles, and as a result, they failed less often. But while I'm suggesting we look for nuances, and I'd also ask questions if there's any other questions. Sorry, before I move on, Fred, I want to ask if there's any questions that I've missed that might be worth answering now.
There were a couple of them. If you scroll down, I think you answered the ones about the creation of the Weibull or the probability plotting paper. You got the Weibull one. A few people commented on techniques like median ranks and others. You're focusing only on the manual method, but this translates to software, right? That the really only difference is how you draw that line. If the computer does it using median ranks or maximum likelihood or things like that. Correct.
And yeah, and I don't know if I'm getting some audience questions at least. I don't know if I'm getting all of them through the chat box, but yeah, that's correct. We're going to go into how this relates to software tools that do probability plotting. And the median rank approach is covered in separate lessons as well. Sorry, Fred, did I miss something?
No, and then I think did you see the one that had somebody said if they go the first and last point, it's a bad fit?
Sorry, yes, now I can see that.
Okay.
Yeah, so if you essentially choose 2 data points, obviously that's almost, in a way, that's throwing away the 98 other data points. You don't simply just do the first and last one, and I'm going to address that question in greater detail and why that's a bad idea later on. I'm actually going to have some diagrams. So I'll come back to that, Fred, if that's okay.
All right, good. And yeah, one of the things that I'm going to jump in just for a second, Chris, is
sure.
People mentioned the different software packages. Years ago, a friend of mine and we realized we had like 6 different software packages that fit curves to do Weibull plotting, basically. And so we shared a data set and we tried it on all 6 different packages and we got 6 different answers. They were similar, but different. Yeah.
I'm going to ask you to hold that thought because I'm going to address that very specifically too.
Okay, good.
No worries. So, but before I do that, I'm going to move on to this little section, which is don't try and see things that aren't there. So I'm going to go back to the data points we had at the data set we had at the very start of the lesson. You can see here are the data points, and I'm going to draw your attention to these little, what might be their own little straight lines here. Now, I've seen many people argue that plots that look like this show almost definitively that we have a couple of little different sorts of failure modes or failure types in these regions over here because they create their own straight lines. This data set was completely randomly generated by a computer based on a Weibull distribution with a shape parameter of 5 and a scale parameter of 2. So this is, as let's say, as pure as you can get for 100 data points. And these sorts of little perturbations are routinely seen in probability plotting, especially at small CDF values. What do I mean by that? Well, the small CDF values and the small random variable values are the values that occur at or close to the origin of your chart. And you can see here that going from 0.5 to 5% takes up a whole lot of real estate on your y-axis, as does going from 0.5 to 0.8 with respect to the horizontal axis. And we should also point out that this is a region that we're typically most interested in, because we're typically after things like time to 5% of our systems failing for warranty stuff like that, or we're typically interested in no more than 5% of our things failing with respect to servicing intervals, so on and so forth. So we're typically not interested in working out when most of our systems have failed. We're typically interested in finding out when a small enough tolerable fraction have failed that then would initiate us to do something about it. So this is almost the most important part of our probability plot. But there's inherent inaccuracies with our plotting techniques. These are points which you put on a chart, but we're not going to go through the mathematics now, but there is errors associated with estimating these CDF values. And if we go through the math, and if we try and work out what the size of these errors are, and try and scale our dots accordingly, this is what we get coming through very soon, hopefully. So each one of these circles has now been scaled to represent the statistical inaccuracies of using that particular data point to estimate where our line on our probability plot needs to be, simply because failure or whatever random process is random. And the reason why the one down the bottom left-hand corner is so big is because of that scaling effect I told you about, where a tiniest deviation from 0.5 to 1% is about the same distance from 50 to 80% on our CDF curve. So when you're looking at these charts for lines, you just need to understand that each of these data points are themselves inaccurate. So hopefully this goes back to our question that somebody asked earlier about using the first and last data points and drawing a straight line between those two. Those data points are estimates of the CDF value at that particular point in time. And hopefully you can see by the size of these circles that there is no such thing as a single data point. Those data points are themselves representing an estimate of the CDF at that point. So we need to always understand the confidence we have in our on our results. And I can see a question, an audience question, which is a statement about which software package does things well. Well, we're going to start looking at what software packages can do for us. But because we are typically not interested in the line of best fit, we want to know where the line is that represents our perhaps most conservative assessment of our time to failure or CDF curve. So we can put these data points in software and say, hey, software, tell us the region where you're 90% confident that the real line or real CDF curve goes through. And you should be able to see on your screen now this shaded region, which in this case is the 90% confidence interval region. So we don't really want to get too fast about the line of best fit anymore. The line of best fit will help us understand if the underlying probability distribution is a good candidate for that particular random process. But once we've gone through that process, we really need to put confidence bounds on the analysis, and we can't do that using the human brain. We certainly can get software to give us these figures here. Give us these confidence intervals, as you can see here. And you can, again, the reason why they look curved is because of that scaling effect. So the confidence interval region seems to be narrower at around this 50-60% region, which is where you have big changes in the CDF value with minimal changes in how far up the y-axis you go. But as you move further away, you have that scaling effect, which means the same step in any direction represents a huge change, a huge leap up and down your y-axis. So your confidence increases as you have more data or information. But here we go, Fred. You talked about different software packages making tons of assumptions to try and give you these confidence bounds. So if we take the same data set, put these numbers into a software package, you'll get this confidence or confidence interval like this. And most of them are based, most software applications use an approach based on what we call a Fisher information matrix to create these this confidence interval region, which has about 6 different assumptions, which become weaker and weaker in certain areas. Now, there is one way to work out what the true confidence bounds are, and this is what the confidence bounds look like based on the likelihood function. In this case, I ran a 10 million Markov chain Monte Carlo simulation approach to get the true confidence bounds for this data set here. And this is so accurate that with 10 million simulations that the discrepancies in the boundaries of this confidence interval with these dotted lines would be tinier than a little dot within each line itself. So this is what the confidence interval region looks like in practice compared to what most software applications yield in response. And the reason why there's variations from different software packages from one software package to another is that they have different approaches, different assumptions, and different calculation steps to deal with those assumptions. But things get worse the less information you have. So let's just say you have 4 data points, which is not a lot of information. You use a Fisher information matrix approach, you get this confidence interval region here, which is truly horrific. You can see here that the upper and lower confidence bounds actually have a negative slope, which is statistically impossible. It is impossible for the upper confidence bound on the CDF to decrease as time goes on. That's roughly analogous to your product having a smaller chance of failure as you use your product more and more often. So let's compare this horrific confidence interval region that software packages will give you with the true one. And this is what it looks like. So if, and I'll answer a couple of questions in a minute. I can see there's a couple of really relevant ones, so just hold on to those that desire to have the answer. You can see here that this is the true, the dotted lines represent the true confidence interval region, again, using the same approach. So not only is our software confidence interval very statistically invalid, you can't have things curving down, just not possible, but it's wrong. It moves away from what the true confidence interval will be, and it introduces a lot more uncertainty. If we were able to get the true confidence values from the start, you can see that because those confidence bounds are a lot closer, those dotted lines are a lot closer together, we have a lot less uncertainty. So coming back to the few questions, is Markov chain Monte Carlo pretty much like the Fisher model? The answer is no. The Markov chain Monte Carlo simulation approach takes the raw likelihood function and uses that to create, in this case, 10 million sample CDF lines, in which we then use to create upper and lower confidence bounds. The Fisher information model, again, this might be going a little bit too nerdy, is you create this model which is create a matrix which different elements of that matrix are different second derivatives of the negative of the logarithm of the likelihood function. You take the inverse of that matrix, and then it gives you the variance estimates for our parameters. And then most assumptions thereafter, most software applications thereafter assume that we then use a normal distribution to describe the likelihood function, so on and so forth, which is where all these errors and inaccuracies come from. The Fisher information matrix approach only works if the distribution you're modeling is a normal distribution. Again, that's a topic of an entirely different lesson, but they're very different approaches. One allows you to achieve whatever accuracy you set out to achieve, and the other, well, you really need to be careful. So the question I would ask everyone is, if you're using software, do you know what assumptions your probability plotting software makes? And it's a very valid question, because if we go back to our charts here, you can see that the region we're typically most interested in, where up to 5% of our things have failed, is the region where our confidence intervals go out the most. And it's also the region where, if there's going to be divergence from our software confidence interval region with respect to the true confidence interval region, we tend to see it down in this region more than most others. And that's a problem. It's all well and good to say, yes, for the majority of data points or the majority of our probability plot, they tend to overlap. That's great, but we're typically only interested in the bits down near to our origin. So I'm going to go back to this one here, and you can see that we have, in this case, a lot more information, which is why there's a better overlap between the approximate confidence interval region and the true confidence interval region. But where there is discrepancy, it occurs down here, which is the money region for most products, most systems, most organizations. This is the area we care about the most. So on that note, do you know what assumptions your probability plotting software makes? It's an open question. It's something you need to be aware of. If you have the coding skills to do it, you can potentially create your own code in MATLAB or something similar to really get the true confidence intervals for a Weibull plot or any other sort of plot. And the good thing about that is they tend to not only be more accurate, but they do away with the positive bias of our software confidence interval region, which tends to overstate the unreliability. So a really easy way to improve the reliability or the apparent reliability of your system is to use the true confidence interval region. It's more accurate and it's typically lower. But on that note, I think I must apologize. I sort of struggled to answer all the relay questions as we went through. Are there any further questions about probability plotting, or is there anything you want to go back to and cover in greater detail? Is there anything coming through, Fred?
No, I don't see any at the moment. Give everybody a chance to hit their keyboard.
Yep.
So, I mean, we could go back to using probability plotting paper, right? Although the software, if you've got enough data, I think goes back to that question on sample size, right? Mm-hmm. So my thought was if you had 20 failures or 20 data points, essentially, is that enough, or how is that? I'm going with the assumption that more is better, but I'm making an assumption there.
Well, I would agree with that. So I'm going to go back to like this chart here. If we focus on the dotted lines, which are the true confidence interval, which is a true confidence interval region for our plot, you can see that the distance between the upper and lower confidence band is relatively small. If we then go to the example where we only had 4 data points, again asking everyone to look at the dotted lines here, which are the true confidence bands, you can see there's a big spread across the confidence interval region, especially down here around the 5% of product failure mark. So how much data is enough? Well, it depends what your risk tolerance is, because you might have 4 data points, and that creates a huge confidence interval region, but because those 4 data points, they might represent unbelievably good reliability characteristics. They might surprise you. They could be failures that occurred so far beyond what you expected to get or to observe that the lower confidence band is actually pretty good. So it's all about your confidence in your results. So the question about how many data points you need to have is a relatively open-ended question. If the reliability performance of your product is somewhat close to your requirements or specifications, you need to have more data, because you need to bring that confidence way in, because they're relatively close. But if the performance greatly exceeds your requirements or specification, then you can do with less data, because even though there's less confidence, it's so far beyond your requirement that that's okay. And that brings us back to testing as well. You can really drive down test requirements if you make really reliable stuff. So there's a couple of questions coming through. Let's see. Oh, there's a lot of questions now. Are there any other ways to obtain the confidence interval of Weibull? And the answer is yes, there's tons of ways, but there's realistically only one real way of doing it, and that is there's no theoretical solution to the likelihood function that Weibull distribution creates for data. You have to use a numerical evaluation approach like Markov chain Monte Carlo simulation. But beyond that, as Fred suggested, each different software package has a ton of different assumptions and approximations. That the technical answer to your question is yes, there's tons of different ways of estimating the confidence interval region. There's only one way of doing it well. What software do you think is most accurate most of the time? That's a good question, and I don't have a good answer for that one. I think, Fred, you've already anointed that one as a good question. And the reality is, me personally, I don't use software like commercial software for the reasons I just talked about. I can go in and use create my own code. I've already got my own programs that do this, that give you the exact confidence bounds regardless. So that's the way I go about it. So I don't have a ton of experience with these software packages because I'm aware of their inherent inaccuracies. Another question, there's so many models out there, MLE, reduce bias inspection mode, so on and so forth. Yes, there are, but some of those aren't actually models themselves. For example, maximum likelihood estimation, that means you find, that helps you find the line of best fit based on the most likely set of parameters. So these aren't necessarily models, the ones you put up here, I wouldn't call them models. Some of them are approximation approaches, but there is only one model in this case, and it's based on what we call the likelihood function and how we use that likelihood function to create our confidence interval region. Another question, do I need special software to find the true confidence estimates, or can I use something like Weibull++? Answer is Weibull++ can't do it. One of the reasons is they like repeatability in the confidence intervals. And what I mean by that is the same data you put in on Tuesday, you put the same data in on Thursday, it spits at the same approximate confidence interval values. And technically, the numerical approach, you need to specify an accuracy for these confidence bounds. But the reality is they all use, Relisoft in particular, uses the Fisher information matrix approach or approximation. In fact, they have on their website the theoretical the explanation of how they make these approximations to create the confidence interval regions. Would you mind, another question is, would you mind commenting on the pros and cons of Weibull plotting using time to failure when you're working with repairable systems, repairing to be as good as new? Okay, so what you're talking about there is, that'll be a question that I could, noting we only have a couple of minutes left, that's a question that could be an entirely new webinar in itself. You're talking about a repairable system or a renewal process, in which case you use a non-homogeneous Poisson process model. Now, if I'll go back to the example for the military vehicles, I actually used that approach to model this vehicle over here, which was repairable, and because the event of interest over here on the, well, where time to failure is set at 0 is where we serviced it, and all these dots over here represent failure points as we move from left to right. So you need to use a non-homogeneous Poisson process model, and I would suggest perhaps you could, if you want to email me after this, I can have a more detailed conversation with you after that. Are there any other ways to obtain the confidence interval of Weibull? I think I've answered that one. Could use chi-square, but again, a chi-square is chi-square distribution, for those of you who don't know, is used to approximate the deviation of our estimate of the mean of a random variable that is described by the normal distribution. So essentially, the chi-square is based on an assumption that the deviation or the confidence intervals region is described by a bell curve, which is not always true. Are there studies on what sort of simulations can give the most accurate bounds, or it also depends on the type of data, so on and so forth? Well, I'm not sure I follow the question, because and I may have given the term simulation can be a little bit scary, but MCMC is, for all intents and purposes, Markov chain Monte Carlo simulation, for all intents and purposes, is precisely accurate. If you want to get it down to 10 microns, if you want to get to the final answers, the confidence bound estimates within, a millionth of 1% from the true value, you just simply do more simulations. So you keep throwing simulations until you know the accuracy is within a pixel of the line on your screen, and that's how you get the true confidence bounds. There's also difference on complexity and price for software. Some of them are more expensive. That is true, but not really related to accuracy, I would agree. And often you are paying for functionality, such as being able to import data or having that software package integrate with another software suite. So, audience question, good idea for a webinar, non-homogeneous Poisson process model. Fred, we'll take note of that one. And I see that a lot of people are saying thank you and au revoir, so I sense people need to go back to their lives, and the number of questions coming in are wearing out, trickling down. So before we say lose everyone, thank you very much for taking the time to listen to me rabbit on about probability plotting. And if there is any more information, any further questions, please do not hesitate to ask. Another question came up about materials. Yes, slides will be available on Ascendo Reliability very, very soon, if not already. So yes, but please do not hesitate to contact me directly. Email me if you've got any further questions, because probability plotting is one of the things that we assume is perfect. We assume is already done. We assume is a process that we know intimately, but I don't think we do, and we are doing ourselves a disservice as reliability engineers. But are there any last questions, Fred, that I've missed?
No, lots of thanks. Very helpful, very informative. That kind of stuff's coming through. So I think you're getting the round of applause at the moment here.
That's right. So we're busy. We need to go away and do other things now.
Yeah.
Which I understand. Yeah.
No. All right. Well, cool. Thanks so much, Chris. And do you have a plan for what your next webinar is going to be next month?
I have a short list, and I will be announcing that shortly.
All right, cool. And we'll look forward to that. So thanks everybody for bearing with us. There was a little bit of audio trouble at the start for some. And so hopefully everybody that got it sorted and brought in. We need to fix the chat window. I don't know why that's not working. So I've got to call into support to sort that out, and because that's usually a big part of how we do our webinars. And so we'll see if we can get that fixed. And so with that, Chris, I think we'll close it off, and we'll talk to you in a couple of weeks when I do a webinar. Not as beautiful of graphics though, so I got to up my game a little bit. But we'll see you next month for your next webinar, and we'll watch for the announcements. Thanks again, Chris.
Thank you very much. Thanks for joining us.